So I'm starting recording now. Okay, welcome everyone to this week's quantum seminar. Today we have our very own Cai Waegell.
Hey everyone.
The title sounds now slightly less provocative than it did before, but it's going to tell us about generalizing Bell's theorem and possibly contextuality theories. So,
yeah, the title is modified slightly, but really it's still about what I said before. So yeah, I'm going to talk about generalizing the original theorem of Bell by formalizing what the assumptions that really go into the theorem are. The original theorem just assumes that quantum predictions are correct, and we want to generalize that to get to a theory that does not assume that. So this is kind of where we start. They'll give this theorem that a lot of people interpret to say that nature is non-local, but really what Bell did was to give a list of assumptions that have to be true, or that would all have to be true, and show that one of them must be violated. So local causality is one of the assumptions that he shows could be violated, but some notion of free choice of measurement settings is another one. And then he was assuming a type of quantum theory where there's really only one world and one outcome. But the first thing we want to do is generalize this away from assuming that quantum theory is correct and just to base our assumptions only on what the empirical facts that we observe in the universe actually are. So we want to come up with a generalized list that we can apply to any possible theory of the universe that's supposed to be consistent with the empirical facts and show that in that list of assumptions, one of them has to be violated. So in order to do that, we're going to have to come up with some new assumptions, and we're also going to have to revisit some of the problems with the old formulations of the assumptions and make sure we get everything straight. Okay, so this is just a kind of a tease. This is a list of all the assumptions that we're going to work out. So I'm going to go through all of this later. But to give you a quick summary here, we've separated local causality into locality and causality. And you see that causality doesn't actually appear in this list. We can define locality really only in terms of separability of facts. And I'll unpack a little bit more what facts are supposed to mean. But in short, if a fact that every system needs to have a physical description in whatever theory of the universe you've got, that description is going to be a list of facts. And if those facts refer to systems in space-time, then we say those facts are in space-time at all the places where the system is. And so that allows us to define a notion of locality by saying that if a fact is non-separable, meaning that it can't be broken up into separate facts, then it has to be constrained to live on one or more events on a world line, so that it can be part of a cause that propagates along some world line, but it can't ever exist in two space-like separated places. Okay, the biggest one I would address is really no-superdeterminism. I'll come back to this a lot more, and this language is probably going to seem confusing right now. But the idea is that we want something that's going to work in a universe where we don't really actually have to rely on probability theory. And so we're going to define sort of the input-output structure that any system has to have in response to interventions. And it's going to be a constraint on that allows us to define a proper notion of independence between the system and the other system that's doing some intervention upon it. Because of this definition, we actually open up a retrocausal explanation. So there are other definitions of no-superdeterminism that more or less catch no-retrocausality, but they have other problems, which I'm going to come back to. But with this definition, we need to add a separate no-retrocausality axiom that says that whatever this description is, it also doesn't contain any information about what the future interventions are going to be. It has to be independent of future causes. Okay, these next two are really about the assumption that Bell made that quantum theory is correct. So if you assume the predictions are correct out the gate, then you don't need these two axioms. But if you want to start with the empirical data, then you need them both. So the first one says, if I've collected a bunch of data and I see something that appears to be true most of the time, but there are a few cases in my data where it seems not to be true, then if the fraction of those is sufficiently low, I'll assume that they are only due to experimental noise. And so the generalization that I would make about my data is actually true. So the philosophy example is that if I have observed with high enough probability that all frogs are green, and then I happen to see like a blue frog, it's safe to assume if there are few enough of the blue frogs that they were not really blue. They were just that my experiment had some noise or error in it. And so maybe the frogs were spray painted or there was something wrong with my detector. But really, the generalization that all frogs are green is true. I know that's not a real generalization in the real world, but it's sort of a philosophical example of what this point means. And then the next step is about induction from what we've decided is true in our limited empirical experience, to extrapolate from that what is true in all future experiences. So if we have seen a finite sample of frogs and we've concluded that all of them are green, we will conclude that any future frog that we see is also green, and that if we see a blue one, it's because of noise in the future. So those are kind of the two core assumptions of all modern science, and the fact that we have all this technology that works is sort of constantly verifying that these are good ideas. Okay, this next one is probably less understood, no memory erasure. So this has to do with the actual empirical facts of the experiment. After a Bell experiment is done, the parties agree that entanglement correlations have been obeyed, but they can only check that when they get together locally. And so one explanation of Bell's theorem is that all of the outcomes are independent, and then choose Alice to be the one that's in control. So then when Bob comes along, Alice just erases Bob's memory, and any other physical system where the memory was recorded is also erased and rewritten to match her correlation. And if there were other parties involved, the same thing would happen. So Alice would erase Charlie and do the same thing. And then at the end, all of the empirical observations will match with what the quantum predictions are, but they won't match with what all of the agents actually experienced when they got their measurement outcomes at space-like separation, because some of those can have been erased. But either way, this will produce all of the correct physical correlations. The last one is the assumption that there's only one world, that when a measurement occurs, there's only one outcome, one observer, there's a single definite outcome in that world, so we're going to have a global ontology. All right, so now let's go in and unpack some of these a little bit more carefully. So
1 second, we have a question here.
Cai, before you go on, can we ask questions about this list of assumptions?
Yes, though I'm going to go through them all in more detail, so you might want to just wait until I get to my details. But if you want to ask questions now, go ahead. Yeah.
Okay, maybe just a larger point. Usually in Bell's theorem, there's some kind of realism assumption, but this does not show up on your list. Can you tell us why?
We don't need it. Yeah, we're going to be able to do the whole argument with just the list I gave you. And realism is also kind of slippery. A lot of people tend to mean one world realism. So you might say that realism is tucked in there with one world.
You might say pre-existing properties are objectively.
Yeah, so I'm actually not going to assume that, because we're going to derive it. That's something that you don't have to assume. We'll get there halfway through the talk. So.
Okay, all right. I'll hold the other questions till later. Thanks.
Okay. All right. So yeah, we can certainly derive probability theories based on what we see in the lab, what an observer sees, and then we're certainly going to end up with some notion of randomness. Actually, this slide got moved in order, so having that comment here doesn't make as much sense as it did when I first wrote these. You'll see why in a minute when I talk about probability theories. So anyway, we come up with some subjective probability theory based on, like, I'm an observer, I'm in the lab, I see data, I think there's noise. I come up with a criteria for discarding outliers, and then I conclude that those are the blue frogs, they don't really matter. The frogs were all green. So that's this first step of noise negligibility. So we formalize this as an axiom that if we've seen enough green frogs and very few blue frogs, we can safely assume the blue frogs are an aberration and don't really represent anything that's physically going on at the underlying level of nature. And then the second one is the inductive skepticism argument. So we have to make the assumption that whatever thing we've concluded based on our finite sample of data is actually really true. And again, we build technology, and the technology in some sense is constantly testing these principles. And so the fact that the technology all continues to work is evidence that this approach is successful. So we formalize that as an axiom as well, that it is valid in some cases to make this full generalization based on some restricted generalization, like a finite set of frogs that you looked at. Okay, so we need both of these to conclude from empirical observations that any fact is completely general. And we define this notion of empirical plausibility. So an occurrence that in nature is empirically plausible if it's consistent with any general fact. So this just says that frogs are green. Only green frogs are empirically plausible based on what we just said. And any other color of frog is empirically implausible. So again, what we mean now is that it's implausible at the underlying level of the theory. We might still say, I make it, there really is a green frog, but somehow it gets painted blue or my detector fails. So we're not saying that it's no longer possible to see a blue frog, just that we're going to assume that the underlying thing that is in the story that nature is telling is really a green frog. All right, this brings us to one of the main issues that we have to fix. So there's a problem with probability theory that we have to address. Bell, actually made this comment in La Nouvelle Cuisine that he's given a clear notion of what he wants local causality to be about, and then he introduces mathematics to try and characterize it, and is worried that this step here should be regarded with suspicion, and that one's likely to throw out the baby with the bathwater. I think he was right to worry, but it's interesting because the equation he came up with, I think, actually does capture the right idea. And part of the direction we go with this is not really exactly to do what he thought, but it is to get rid of probability theory and to separate causality out from the argument. So the first case here, this is the standard formulation of factorizability that Bell used for local causality. And it just says that the probability of getting some outcomes for some settings, given a local hidden variable lambda, can always be separated into independent probabilities for getting the outcome for setting y, outcome b for setting y, and times the outcome a for setting x. So the trouble is that if I have an ontological theory where there's just nothing random at all, then given the lambda, the true ontic state of that theory, the probability that anything happens is just 1. And the probability that anything that doesn't happen in that world occurs is just 0. So in that world where I have full determinism, it doesn't have to be determinism, it just has to be non-random. That's actually all that matters. This is impossible to violate. I'm always going to be able to satisfy this equation. And so if I have a theory that has no randomness and it is genuinely non-local, this will fail to detect it. So a kind of a silly example would be Bohmian mechanics with a non-random initial condition and the God's eye perspective. I know what the hidden variables are. I know what the wave function is. There's nothing random happening in this theory. And so I can predict with certainty absolutely everything that's going to happen in that theory, given that information. So all these probabilities are 1 for the things that actually happen in the theory, and it's manifestly non-local. The theory is explicitly, sending information non-locally, but this just fails to detect that. Okay, the similar problem for the usual notions of measurement independence. These are formulated in terms of conditionals where the probability of x, if I know lambda, will be different than the probability of x if I don't know lambda. But again, these probabilities are all going to be 0 and 1, and so it's going to be impossible to violate any of these equations. So you can have a theory that's got very conspiratorial stuff going on. So for example, a goblin in the past light cone of your whole Bell experiment, sends out magical signals locally that control what your measurement settings are going to be and prepare the hidden variable for the state. And so everything is dependent in the way that is supposed to not be happening if you have free choice of measurement settings. But nevertheless, these equations will never detect it. So we have these standard formulations of what it means for measurements to be independent and what it means for probabilities to be separable, or for probabilities to be locally causal, I guess. But either way, both of these just fail if we try to consider any general theory, because in our list of general theories, there are going to be non-random universes that we have to consider as well.
Excuse me, Cai, we have a question in the room for you.
Yep.
I'm not sure, Cai, if you can hear me from here.
Not well. Maybe you can speak up a little more.
Yeah. So I was wondering, regarding this claim that you made regarding pilot wave theory or Bohmian mechanics, that one cannot use the condition PAP given XY lambda equals to PY given lambda. But I think that pilot wave theory can be analyzed in these terms of these probabilities, and the fact that the theory is completely non-random or deterministic does not affect the discussion.
Yeah, so this actually gets to the heart of what I'm going to do with the no-superdeterminism axiom. So it depends what you mean by these probability distributions. If these are subjective probability distributions that an observer has, then these can be violated. But if we have a God's eye perspective and we just know the whole hidden variable theory, then there's nothing random that happens in this universe. Absolutely, if you know the initial condition and the laws, then the probability of a given measurement setting being y is 1, and the outcome being b equals +1 is 1. You know every single thing that's going to happen. So all of the empirical facts are like a fixed painting throughout space and time. And so you can point to that painting and say, that's the thing that happens with probability 1. And if there's something that's not in the painting, that's probability 0. So it matters what you're talking about. So I'm talking about the probability at the ontological level, the real underlying description of nature.
Yeah, so if you consider like a deterministic theory, like pilot wave theory, so at the ontological level, the probabilities are all either zeros and ones. But then we can have like a frequentist description, like not a Bayesian description, where you collect like.
Sorry, can you repeat that last sentence? I couldn't hear you.
So I'm saying that let's consider like pilot wave theory, where there are no probabilities except zeros and ones at the ontological level.
Yep.
So now, even in this case, I think like if you do not need to have a less subjective interpretation of probability to go forward with your to violate this argument that you're proposing. We can have a frequentist description. We can have an ensemble of runs, and then we can like talk about whether for that ensemble.
Right, but that frequentist description you're talking about is inherently subjective, because the only way you derive it is take that painting and say, I'm an observer who tracks through that painting, and I've seen a finite sample of data. And from my finite sample of data, and given the fact that I am uncertain about the outcome of the next one, I will come up with a probability theory, a frequentist probability theory. But the God's eye perspective just has none of that uncertainty. They know exactly what will happen next. Maybe another example that I can give is actually, this came up in a conversation yesterday, is forget about Bohmian mechanics for a second, and just imagine a world in which non-local Newtonian gravity is true. But it's completely deterministic. There's nothing random happening, even for the observers. The observer is completely certain about everything that's going to happen. So there's no thing where like I'm not sure what's going to happen next. There's going to be some random event. Everything is just sort of straightforward billiard balls. I can see all the stuff that's going to happen, and I can say that theory has an explicitly non-local interaction in it, and you will never be able to detect it with this equation. Did that answer your question?
So I was thinking like in this manner, like suppose you have like classical like statistical mechanics. So classical everything is deterministic, but that does not mean that there are no probabilities in classical statistics.
No, I completely agree, and that's what I'm going to get at. Is kind of, but there's something very subtle going on here, that we have to define these internal probability theories based on some number space, and we need a way to define what that number space is, and that has to be coming out from inside that deterministic theory. And that's what I'm going to get to. That's really what I think our no superdeterminism axiom is about, is kind of the most general way to define what that number space should be.
Okay. It's not 100% clear to me, but I will be waiting for your no superdeterminism assumption, and maybe it will become clear. Yeah.
Okay, yeah, hopefully, yeah, we will see. Yeah, I know this point is contentious. This is not the way that people normally look at these equations. From having this God's eye perspective where you just know the whole ontic state. But that's the thing, is if you have a universe that does not have ontological randomness, the actual description of that universe doesn't produce random events, then it is true that all these probabilities are simply 0 and 1 in any theory like that at the ontological level. Okay, I guess I already talked about measurement independence. Let's go on. So this is just Waegell, kind of what he was saying about the same stuff. So this is also from La Nouvelle Cuisine. He was talking more about measurement independence here than locality. So that's really what this quote is about. But yeah, he's talking specifically about how you would come up with a notion of free variables if you have a universe where there is just actually no randomness, that all randomness is illusory. And you still want to come up with some notion of randomness and independence. And so he's saying you have a superdeterministic theory where things are locally causal, but we have something like the conspiratorial goblin that I described that sets everything up in advance so things are dependent. But he didn't like that kind of theory. Again, that is a viable explanation. It's one of the ways out of this list of assumptions, is that there are these superdeterministic correlations. But anyway, what he was really interested in was, I think, what we're trying to do now, which was take a theory that has no randomness, and then from within that formally define how are you going to get out a proper probability theory that gives you enough randomness so that you can say your variables are free. That's really what I think this is actually about. And so he doesn't have a theorem about that, but I think we do. I think that's kind of what we've got here. Okay, so how do we do it? So we need a notion of independence that's going to work even in this non-random universe. We don't want to make any use of probability theory at all. So instead of probability theory, we'll come up with this functional input-output structure that describes how a system behaves. And the existence of that structure is going to be required. This is actually something that I'm not totally sure we need, but right now we're just going to say that it's required, that in order to satisfy our axiom of no superdeterminism, a system has to have this input-output structure that describes its behavior. So then independence can be defined by insisting that the structure can accept any input consistent with past empirical facts, and that it assigns an output that's empirically consistent with all the occurrences of that input. So this is kind of where, this is the meat of the new theorem right here. So we're saying that if there are a bunch of, if I have some system and I've done lots of experiments with it and I've seen lots of different types of interventions that occur on that system, then all of those are empirically plausible inputs. So that system has to have, in its physical description, a response to all those things that can happen to it. And then likewise, in all those cases, when those things did happen, I saw how the system responded. It did certain things. And so the things that it does in response to the input also have to be consistent with the things that I've seen in the past occurrences of that thing. So now I'm saying that on just one run of an experiment, there has to be a complete description that says, the physical sort of rules that describe that system have to say, I can accept any one of these inputs and I will return any one of these outputs, and they will correspond to, the outputs will all be things that are consistent with, real physical observations in the past. Now we have inputs in this list of outputs, but in a world there's no randomness, only one of them happens. So it almost doesn't matter. There's no actual probability selection over these. So there's no meaningful notion of probability about how they get chosen. So again, what's really important here is that I have a physical description of the system, and in that description, I just don't know anything about what the interventions are going to be. There's nothing that entails one from the other. So so one way this could be violated is that I have my list for a system, but there's some empirical intervention that's simply missing from the list. So what that means if it's missing from the list, because this is the underlying description of nature, is that intervention cannot happen. That for whatever reason, it's impossible. And that means now that my description of this system entails something about how other systems are going to intervene on it that it really shouldn't be able to. So again, if we formally define it so that the physical laws that describe each system don't know anything about what the other interventions are going to be, we get a notion of independence that's sort of like what Bell was talking about with pseudo-randomness. That even though this is fully deterministic, there is no random, or it could be fully deterministic, and without randomness, we can still get a notion that there's, there are two independent pieces of information. And in some sense, this is really intuitive. Like we imagine that if I, encode something in one computer and then I encode something in another computer, there really are separate pieces of information in those two computers. Maybe they're the same because they had some past common cause. And so we have to talk about our goblins and stuff, but we want to have separate pieces of information and, in these two places, and we want it to be the case that they don't entail each other. So that's really what the independence is going to be about. So I hope that that's clarified some of the questions people were asking about what we're trying to do. And so again, really, every theory that provides a subjective probability theory is really just saying, all the things that I say have non-zero probability are in my list of empirical responses, and all of the inputs that I can accept are in my list of empirical interventions that can happen, empirically plausible interventions. Okay, so we call this conspiratorial. This is basically a case where, for example, Alice thinks that she's free to choose a certain measurement setting, but she's not because it's missing from the description of nature. And the reasons that she can't choose it are, there's two different ways it could happen. One is that the setting simply doesn't, the intervention is missing from the description. So it's just impossible for her to make the intervention. And the other would be that the response to the intervention is something that is empirically implausible. So like the system has a list of things that can happen, but there's one that never actually happens in nature. And somehow that's always hidden away. Alice, it's always the case that Alice has chosen a different setting. And so, if she happens to choose this one setting, something really bizarre happens, like a unicorn pops into the lab. But for whatever reason, even though that's in the physical laws of the nature, it is arranged so that Alice never sees the unicorn. That's also conspiratorial. So we're claiming that the physical laws are not hiding unicorns, and that all of the interventions that we think we can make on a system are actually part of the description of that system. Okay. So this gets formalized as our action. So we can say no-superdeterminism is that the complete present physical description of a system has to determine an empirically plausible response to any empirically plausible intervention by another system. So this is the summary of that whole input-output structure discussion. And remember that empirically plausible was defined based on our empirical facts and our noise-negligibility and no-inductive skepticism axioms. And as I mentioned, if you know the Parisian zigzag, there's a retrocausal model that can get around this. So to give a quick summary of how that works, it's going to happen in a sequence. I'm going to have Alice measure and then send some information back in time to the source, and that's going to go to Bob. So the initial description for Alice is just the Bell state. And so it has an empirically plausible response to any intervention. No matter what setting she chooses, she's going to get 50% up and 50% down. And the responses can be probabilistic in a general theory. So she has a definite description of what's going to happen. And now her outcome, she chooses a setting, she gets an outcome, the information gets sent back in time to the source. And that effectively just collapses the state that goes to Bob into a single qubit state. So then that single qubit state gets sent to Bob, and we know exactly what happens for any setting that he measures on that state. And so again, there was a description for both Alice's measurement setting and Bob's measurement setting that satisfied no superdeterminism, but it violated no retrocausality because it included information about Alice's setting and outcome back in the past. So we actually need to have both of these axioms separate now, whereas in many of the arguments, like the independence ones based on probability theory, this is pretty much captured by the original statement. But now we've shown that there are going to be these non-random universes where it doesn't capture it, and so we need to fix it up somehow. Okay, the next thing to talk about is locality and causality. So his original idea was centered on local causality, and it was really based on special relativity. So he had bounded regions of space-time and a screening off of the future light cone or the past light cone of some event, so that you could really say, I've formally got all of the things that can causally affect that event, given the causal rules of special relativity. But causality is actually kind of a vague notion. It really depends on what theory you're talking about. You have to give a lot of information to say what the causality modeled in your theory is. And so there are lots of authors who have claimed to have loopholes in Bell's theorem by saying that their argument doesn't violate causality. But most of them acknowledge that it does violate factorizability, that they end up with descriptions that are not separable, but they've sort of carefully tried to redefine what local causality means so that it's not violated, even though this separability is violated. And that's true of like the many worlds people, the Oxford Everettians, and like Lev's notion of many worlds, Lev Weidmann's notion of many worlds. The issue basically is that causality is just vague, and it actually is not needed for the argument, so we take it out. So we're really just going to focus on locality, because locality is really about this factorizability. And again, the factorizability was something we were using that came from probability theory, but the underlying point of it is separability, that I can give a separate description of each of these two objects. And so again, we're focusing on the system's description, underlying description of the system, and we're saying that this description and that description are separate and independent, and that the facts in each of them are there are no non-separable facts that bridge between them. So they're completely separate facts, and they don't refer to each other. So this is how we define this notion of facts. We have a system as a list of facts, the description is a list of facts. Again, if they refer to stuff in space-time, then that means that the fact is in space-time at the location. So not all facts about a universe have to actually refer to space-time, but if they do, we say that they're in space-time. And then, an unseparable fact is just one that can't be broken down into smaller facts. And that you can just define it to be that way. Here is a fact that stands alone. An example of this kind of thing, which appears in various places, is an attempt to try and say that the correlation between two entangled particles is the non-separable fact, even though the outcomes will still be random. And this just, it's one of these ways people try to get out of local causality, but in the end, it still violates the underlying principle of locality because you've got something non-separable.
Kai, I'm a little bit confused about that last part. Can you go
Okay.
back?
Yeah.
So normally I'm thinking about separability in terms of locations in space-time. And
Yeah.
at the end, you said a non-separable fact is defined such that it cannot be separated into multiple facts that do not refer to one another.
Yeah,
What
space.
has that to do with space-time?
Nothing yet. Yeah, that's totally general. And I'm going to put it. What we're going to talk about it being in space-time in the axiom. So that's what's next.
Okay.
So now we say, given that we've defined non-separable facts completely abstractly, whether they can be in space-time or not. Now we say, if you've got a non-separable fact and you say it's in space-time, or it's defined so that it refers to objects in space-time, then it has to be confined to one or more events along a single time-like or light-like world line. So it can't be like a tachyon because that extends along a space-like world line. So we can have objects that stretch out along a world line, and that's what really a cause has to be. I'll talk about that in just a second. But in general, to obey locality, you have to have objects that are essentially isolated to their own events in space-time. And they can, if there's nothing else changing them, that it can propagate forward along a world line from that event, and the fact won't have undergone any changes. But if they're interacting, then it could be. So this just says that the full description of a system, that if I have any non-separable facts at all, they don't connect two things that are space-like separated. That non-separable fact is just tied down to this one world line. And so if you've got a fact that's defined to be non-separable, and maybe an example would be that, like, I can't define the, I don't know, actually, let's see, what is a good example? Well, I mean, just maybe you could say that, like, the definition of an electron is non-separable. So it has to have its mass and its charge and its spin and various things like that. We don't really know that it's non-separable, but it could be. So we can say that, it only makes sense to have this object and all of these facts are together, and they all live on one world line because that's a localized particle. But I can't try to say that part of the description of a particle is some delocalized thing that's spread out between two world lines. That's forbidden here. And I can't have any object that propagates faster than the speed of light either. Also forbidden here. So yeah, again, for causality, you need to have this notion of extending the facts. So if I want to define a theory with causality, I need to define some directed acyclic graph that has, the events, the causes and effects as vertices, and the arrows really are the causes, actually. So you have outcomes of causal outcomes, which are like the vertices, and then if those things go on to affect some other event, there's a causal arrow that connects that fact to the next event in space-time where it's going to be relevant. So the DAG doesn't actually have to necessarily be in space-time either. You could have a DAG that does things that are retrocausal or does stuff outside of space-time. You can have a very abstract causal structure. But if you want to say that it's locally causal, then it'll have to be the case that all of the causal arrows in the structure that connect things in space-time obey this definition of locality. And I guess the ones that don't, that aren't in space-time are not going to be constrained by the locality definition anyway, because that only refers to facts that are in space-time. So we can have a set of facts that describe the system, and yeah, if we want to make the claim that something is locally causal, we have to first define exactly what we mean by causality, and then we can compare that definition with this definition of locality and come up with our notion. And so this does allow retrocausality. I should point out that we have done nothing to specify what the direction of time should be. It's just about world lines and space-like separation. So you could have something propagating backward along a world line just as well here, and that would not violate this axiom. So the no-retrocausality axiom is the separate thing that stops that if you need to stop it. All right. Yeah, I talked about this one probably enough already, but this is just another loophole that people don't pay a lot of attention to. So yeah, you can have it so that Alice rewrites Bob's memory, and any other device that he's used to record it and encode it, it's written, it all gets erased and rewritten so that everything is consistent with Alice's measurement outcome and the entanglement correlations. This type of erasure for quantum systems is actually routine in information processing and computing, but there's just sort of a general expectation that it does not happen for macroscopic systems or recording devices. If you record information in something sufficiently classical, macroscopic, then it's just not going to be erased in the quantum sense. It won't be undone by the inverse unitary. So we formalize that assumption here just by saying that there's no memory erasure if the system is sufficiently large. And then whatever things happen to encode it are not going to be reversed. And we'll need that for a step in our Bell proof in a little while. Okay, so now we're going to go through an improved version of the Bell theorem based on all these new definitions and axioms. So the basic idea is that we have two or more qubits. They're sent to space-like separated observers who each choose from some set of settings. The choices are supposed to be free or independent or whatever notion of freedom you're looking for. And then they measure the qubit, and each qubit and each setting choice are a mutual space-like separation. So we're going to assume a bunch of the axioms, and in the end, we're going to show that the one world is violated. So that's going to prove our theorem that if you assume all the other ones, one is violated. And actually, there are lots of ways to show that if you assume some other set, you'll violate a different one. But we're only going to do this one particular proof here. So we're going to assume locality. And that tells us that we have no non-separable facts located at two or more space-like separated events. And if we did, that would allow for a non-local entailment between the events. So, something about this one can change what's happening over here for the other one. And so their descriptions will not be independent because of that. So locality rules out this type of non-local entailment. No-superdeterminism says that the descriptions have to be, they have to have proper empirically plausible responses for all empirically plausible interventions. And so again, there's nothing about the description of a system that entails what the interventions are going to be on that system. And so there's no entailment between the system and the setting, the measurement settings that are going to be chosen on it. Those would be superdeterministic entailments, so those don't happen either. Retrocausal entailments would be the case where we have some information that's been sent back in time, and that could also create entailment between the setting and the physical state. So we've ruled those out as well. So now we're going to say this was it. Those are all the types of entailment that we have to worry about. And so if none of those types of entailment exist, then we have completely independent descriptions of these space-like separated regions, and we can just now define each of them as an independent variable. So we're going to say, I've got a variable over here that fully describes all of the contents of this region, and it's completely separate from the variable that describes this other space-like separated region. There's nothing about them that entails one another. Because really, any of these three methods I just went through could create some kind of a dependence between those variables, and that's what we want to avoid. Okay, so we'll define the space-time region for where observer A is going to do her measurements, or we usually call her Alice, screened off by some boundary that includes the incoming qubit and the choice of measurement settings. So in her region, she's already got the choice of setting, and she's got whatever physical state came along with the qubit. And so given that the setting choice was J, we'll let the variable A subscript J represent all of the physical contents of that region. So even if new random stuff is happening in that region, it's all part of what we're saying is the description of A. And the subscript J just tells us what setting was input kind of at that initial boundary for the region. So AJ just represents everything that's in that region, all of the physical content of the region. And then the qubit and AJ together represent the complete, it's both. The qubit is a separate thing. You'll see why it has to be. So AJ represents everything other than the qubit, and the qubit is a separate object because its description has to be independent. So together, those are all the content. Sorry, I was a little bit unclear about that. So whatever, somehow the measurement process occurs, and at the event at the tip of that cone, an outcome pops out, which is +1 or -1. So those are the facts we know about the experiment. They chose a setting, and the measurement process takes some time and it occurs within this region. And at the end, this outcome pops out. And then the same thing happens for observer B with setting K. So we have these independent things happening. Okay, so using the no-superdeterministic definition of this input-output structure, we'll actually formalize that as a function now. We'll say that the qubit is the description of the qubit is a response function Q. The inputs to that are A, which is the complete physical content of the region. So everything that could possibly affect the outcome if local causality is being obeyed. And then that produces this outcome. So we think of the qubit, the qubit's description as being this response function. And so that the Q's now are the descriptions that contain the response functions. And these are purely algebraic statements. I'm not doing anything with probability theory here. Okay, so now we bring in no memory erasure. So Alice or observer A does a measurement and gets an outcome and records it. And observer B does a measurement and gets an outcome and records it. And we're now going to insist that those outcomes they recorded when they were at space-like separation do not change. And so when they meet later and compare their results, the outcomes that they compare will be these same ones they saw when they were at space-like separation, and not, only matching because Bob gets erased or something. Okay, so then when they do meet, they're going to get together and they're going to conclude that the correlations really did exist even before they got together. They're going to meet and they're going to conclude from their memories of what happened that, yeah, I was over here and I got plus, and you were over there and you got plus, and they were correlated. So it sure looks like the entanglement correlations were already obeyed, even though they can't check until they get together. Okay, so this just summarizes all of what I went over. So this is our Bell test. We have a source that produces the two entangled qubits. They get sent off to the two regions. J and K are the measurement settings. And then I've got these bounded regions, RA and RB, which are all of the stuff that can causally affect the outcome lambda. And I characterize what's happening in that region as Q is a response function, and AJ is everything else in that system, in that area, which can be intervening upon the system Q, or on that qubit. And likewise over here, that B and K, which include the setting, represent everything that's intervening upon the qubit description. And the end result is that we get this outcome out. Okay. So now to go through the GHG test, this is going to answer the question that Andrew had asked earlier. So for the GHG test, there are 3 qubits that are prepared. They're sent out to Alice, Bob, and Charlie, who are at space-like separation. Each of them chooses freely, or whatever that means, between settings X and Y, and measures their qubit. If the preparation P obtains, which means that the whole experiment runs, we set it up, we prepare the state, the detectors work, asteroids don't destroy the lab, everything happens, then and we assume no inductive skepticism, then the measurement outcomes are always going to obey these correlations. So these 4 rules again come from we've done this experiment many times. We've seen the fact in the lab that these correlations obtain. We've concluded that our finite set of data represented something which was actually generally true underneath, even though we had some blue frogs in our data that didn't always see exactly this correlation. We're going to ignore those cases. And now we're going to infer that because this has always been true in the past, it's always going to continue to be true. And so whatever the physical description of nature is, it has to obey these rules. It has to produce these correlation rules for the separate measurements that Alice, Bob, and Charlie make, given the memories are not erased. Because again, this comparison only happens locally when Alice, Bob, and Charlie can exchange information, but we're still using their independent response functions, which is the assumption that there was no memory erasure. Okay, so now it follows from those equations that if the interventions are all independent variables, which we went to a lot of trouble to prove that they were, or to show that they were given our assumptions, then on a given run of the experiment, all of these functions have to be constants. And what that actually means is that no other details about the variable A, other than the setting Y, could have changed the value. So if I know the setting is Y and I consider any other possible variation of the physical contents of the region, anything else that could be there in A, like some stuff that was waiting around, maybe like waiting photons or some kind of, historical background that had been set up, whatever it is, it's all part of A, and it has no effect on the outcome. And the proof of that, so this is the outcome dependence or realism proof argument. We didn't need to assume it, we can derive it. It comes from our empirical plausibility assumption. So it comes from the fact that if I have 3 functions of independent variables whose product is a constant, then all of those variables have to be constants as well. Or sorry, all of these functions have to be individually constants as well. That's just a simple algebraic fact. Here's the proof for 2 variables down at the bottom here. So we can just prove that there have to be pre-existing values. So we have essentially derived outcome determinism for this case, that if the entanglement correlations have to obtain, then the individual outcomes have to be prearranged in some sense in order to match that. So now we know there have to be these lambda values. There have to be 6 lambda values that fall within this range. They're either +1 or -1. And we have to assign them to these Qs such that they obey all of these restrictions. That's what we need to do. Okay, so if you do that with just 6 lambdas, obviously it doesn't work. If you know this proof, it's obvious. If you don't know this proof, maybe it's not. But yeah, if you try to put just 6 values in there, all assigned values from +1 and -1, and then you square them all because they all appear twice. They all appear in 2 of these equations here, xax and or qa of ax and qa of ax. So all 6 of these appear twice. And then the product on the left side is -1 because I've got 3 pluses and 1 minus. So I get this contradiction. It's just impossible to choose 6 values for the lambdas that are going to do it. So that tells me I have some kind of contradiction, but I'm actually not quite done yet, because we're going to show now that even given this logical contradiction, there's still a way to actually satisfy this, but it's going to require us to violate the one world assumption. So if instead of insisting that each measurement resulted only in a single outcome, lambda equals +1 or lambda equals -1, we're going to say that each outcome each measurement resulted in both outcomes. There were multiple copies of the observer, some who saw +1, some who saw -1, and they don't see each other. And so that's consistent with, the empirical facts locally. You don't end up seeing copies of yourself branching off, obviously. So if we have many worlds, you don't see the other worlds. And then we can match up these multiple copies later when they meet locally, such that the correlations will be obeyed, and there was no memory erasure or anything required to do it. So this is how it works. It's pretty straightforward. The general case will actually need 8 copies, but I'll talk about that after. So suppose that this is actually what the hidden variable is. Lambda x and lambda y are both multi-valued hidden variables. So there are hidden variables. They are within +1 and -1, but they now say when Alice measures x, there are now 4 copies of her, 2 that got +1, 2 that got -1. When Bob measures x, the same thing. When they measure y, the same thing. So no matter what setting they measure, they always just end up getting half and half results. And that is consistent with the local Born rule probabilities that they experience from the reduced density matrix. So we've matched the Born rule, so far, given that they may not ever actually meet each other and find out what the correlations were. It's just 50-50. And so, if you do it right now, what we've done is we're just doing one run, and we've said that Alice breaks up into half Alice's that get plus and half Alice's that get minus. But if we repeated this many, many times, then that Alice would end up experiencing a frequentist probability, which would be consistent with the Born rule. So we're saying that the Born rule distribution is there already on just one run. Therefore you will uncover it if you do many runs. But it's already there. The whole distribution is there on one run. Okay, now we get Alice, Bob, and Charlie together. They meet up. And again, all the copies are invisible to one another. And so what's going to happen now is that only certain copies of Alice, Bob, and Charlie will see each other. And they'll get matched up so that the correlation is obeyed. So the correlation for the x setting, if they all measured x, was -1. So they get together. And again, if you look in the columns, we have 2 pluses and 2 minuses. And now we just match them up so that this plus Alice meets this plus Bob and this minus Charlie. And that obeys the correlation. This plus Alice meets this minus Bob and this plus Charlie. That obeys the correlation, and so on. So there are all 4 of them get matched up, and they all obey the correlation. And so for every run of this experiment, the Alice, Bob, and Charlie will agree, yes, the correlation was obeyed. And that also is the Born rule probability. The probability that they will get a product -1 is 1. And so this also obeys the Born rule. Now, a slight wrinkle here is that if they measure x and y randomly, there actually are 8 settings they can get, not just these 4. And if they get the other 4, sorry, not these 4 here. If they get the other ones, the results will be uncorrelated, just 50-50 shot of getting any combination of the outcomes. They're only correlated for the GHZ state for these settings here. So if I want to make this general, what I do is I say, okay, instead of only 4 copies, I have 8 copies, 4 pluses, 4 minuses. So that still produces the Born rule probabilities for each of them locally. And now, when I get them together, I now have 8 different matching rules. So if they measured XXX, I do this, and I just have twice as many of each. I double each of these up to match all 8. But now if I've got any of the other settings like YYY, now I just end up with all 8 possible combinations, half of them multiplying to plus, half of them multiplying to minus. And so I produce the correct Born rule probabilities for that case as well. So if I make 8 copies every time, then even if the settings were not from the 4 chosen settings, this will reproduce the correct empirical correlations. So it'll cover every possible case. I only needed 8 copies here because that was all that we needed to match the fractional ratios for the Born rule for this particular case. But for a general case with a general state, the number of copies that you actually need to get the right fractions could be infinite, or it could be extremely large. So this is just a nice, simple case. So really the best way to think about these copies is not that there's really a finite number of them. It's actually that there's a huge number of them and they've been grouped together into a group that are all +1, another group that are all +1, another group that are all -1, and so on. But we can always break those groups down further, and, depending on what state we've actually got, we have to get to match up. So we've shown that we can reproduce all the correlations, and we've explicitly violated the one world axiom. And again, we showed that if we, by assuming all the other axioms and one world, we would get this contradiction. So we wouldn't be able to make that work. But now if we take out the one world assumption, we can get it all to work in the end. Okay, so actually I'll stop here and take questions. I have more to say about contextuality theorems, and I might actually just skip over this because I took more time than I thought I would. This was like the optional part of my talk. Basically, to give the quick tease, if we, using our new no-superdeterminism axiom and some reformulated axioms on contextuality and outcome determinism that include specific specific information about what you'll do if you have a many worlds type theory, you can reformulate the contextuality theorems the same way. And again, you can, take out the assumption of quantum theory. This is not anything new. I mean, Specken's group has been looking at robust contextuality inequalities for quite a while, but you don't have to do quite as much work to add this in. So we can just, this is the list of axioms that you need. The 2 new ones are contextuality, measurement contextuality, and outcome determinism. And I will just skip over how this works. The proofs are not even really that exciting, or there's nothing, sorry, we haven't done anything to refine the proof. It's kind of the same old proof it always was. It's just that we've cleaned up what the axioms are and given a clear explanation of how to deal with, how to talk about this stuff when the worlds are considered. So yeah, there are 2 different kind of classic proofs of the theorem, and there are many other types of proofs as well. But they come down to a parity contradiction, just like the one we saw in the GHC argument. Yeah, I can talk about that more if people have questions, but I'll just stop here. So this is pretty much the conclusion. We've attempted to refine the assumptions of the theorem so that we can put this restriction on any possible candidate theory of the universe that one of these axioms in this list is going to have to be violated. And we've shown that if we eliminate probability theory from the definitions, we end up with more robust definitions, and we can get rid of the extraneous notion of causality, and at least kind of put it into its proper place within these theorems. But you don't need it for the argument. We didn't use it in our refined Bell argument at all. And yeah, we've sort of tried to do the same thing with contextuality theorems. So yeah, I think that it's generally interesting. You can come up with these theorems where you have some list of assumptions, and you can really show that one of the assumptions has to be wrong in your theory of nature. So finding, these are kind of in the category of no-go theorems, but finding a set of theorems like this, which each place different restrictions on any theory of nature, I think is pretty interesting. We sort of can bound the set of possible physical theories by showing that, something that we kind of took for granted as being classically obvious has to be violated in any theory we've got. And if you do this with the contextuality argument, you sort of get like an independent set of, I'll show you in this list. So one in this list of 5 has to be violated, and one in my other list for Bell's theorem has to be violated. There's some overlap, so you could have a theory that violates no-superdeterminism, and that would satisfy both theorems. But if you violate, one world, then you might have to look at what that means for the other axioms here. So you might end up needing to violate one axiom from this theorem and a different axiom from the other theorem, and in some theory of nature. So the more of these types of theorems we have, the more restrictions we're placing on any candidate theory of nature, any post-quantum candidate theory of nature. All right, that's everything I have to say about this. Yes, I'll stop and take questions.
Or raise your hand using the hand raising icon. Is there anybody? Zoom.
Hope that means we made this all clear.
Yeah, Cai, I had a few questions about talk, you said something about Born's rule probabilities. And I'm a little bit confused about both of those statements because the original Bell's theorem.
I think you might be cutting in and out. I don't think I love what you're saying.
Okay, so let me repeat. I said in the beginning of the talk, you said something like the Bell's theorem assumes quantum mechanics, and we want to go beyond.
Yeah, you've cut out again. I'm not sure what's going on.
What I can do. Just try getting really close to the microphone, I guess.
Where is the microphone? It's right here.
Okay. Whose end it's on? We're both on university.
No, yeah, you're frozen. Or maybe not.
Okay. All right. Well, it looks like our
Yeah, we're having a bad connection. I think it's part of the issue here.
Are there any questions in the Zoom room? Any questions for?
Andrew, I'm going to come meet with you, so I can answer your questions in person. They're not for the audience. Kelvin, you've got a question?
Yeah, I mean, I had a thought on a previous question. So Bell's theorem is about theories that are consistent with the predictions of quantum mechanics, and it's trying to say that of those theories, if they satisfy measurement independence, they must be causally non-local. This is a generalization in the sense that it's not merely about theories that are consistent with quantum theory. It's generalizing in the sense that it's about theories that are consistent with our experiences, our actual outcomes that we've experienced. So that's why we need no-inductive skepticism, noise-negligibility in order to get the result. So in response to this concern about the probabilities, you mentioned, hey, imagine we have a Newtonian world where we've just got like Newtonian gravitation. Factorization cannot be used to diagnose the non-locality in a Newtonian world. And I realized that kind of theory is not really in the purview of this proof. This proof is about theories that are consistent with our observations, but in a Newtonian world like that, we don't have the kinds of observations that have led us to believe in the entanglement correlations. So I feel like that kind of world can't be used to respond to the objection that we saw before that Bohmian mechanics, Everett, and so forth can get out the probabilities, which means if that's right, then the challenge is we have to go back to deterministic theories like Everett, like Bohm, and try and say why they can't use their subjective probabilities to plug into factorization and measurement independence. Do you see what I mean?
Yeah, I think that the key difference is what you say. It's about making an argument that the subjective probabilities are not actually good enough to make a claim about what's ontologically going on under the hood.
So my concern now, just to be clear about the concern, is because this generalization of Bell's theorem is about any theory that is consistent with our observations, the current concern is going to be of all theories that have these observations that lead us to believe in quantum theory, there will be some sort of subjective probability theory that you can get out of it just because we've experienced subjectively random results, in which case those probabilities can always be plugged into factorization and measurement independence. That's the concern.
Yeah, I mean, again, I think that we know that if you plug in the empirical probabilities that we experience, that you can violate some of these arguments. But the question I'm really asking is about a universe in which there is, the universe that Bell was talking about, where all randomness is illusory. There is nothing random. There's no variation of any kind. What happens is what happens. And in that universe, what's ontologically going on simply has no probability theory. And so if you're talking about your subjective experience, you're talking about like the frequency with which you've observed, some things in your part of that big painting of empirical facts. But you can't really infer anything about what's ontologically going on from that. I should actually add that I think I forgot to put Kelvin's name on this, and part of this talk is stuff that he and I have not worked on, but he definitely was one of the co-authors and in collaborate. We thought about all of this stuff together. So he should have been on the first slide. That was my mistake.
Okay, do we have one more quick comment or question from anyone? Our internet connection is unstable, apparently.
Yeah.
Otherwise, I think we'll have to close for today. Thank you very much, Cai. I'm sure we have plenty to discuss on this. I don't actually have a speaker for next week. Please. And thanks for coming.
Thanks for listening, everyone.
Thank
Let's
you.
see.
Bye.